Hello students, in this lecture we are going to solve the questions provided in the practice set supplied to you earlier. So let us start without wasting time. Let us start with the solution of the questions of operating system so that you can attempt in your uh, MTE, that is midterm exam, that is going to be held tomorrow. So the first question is, what is a process control block? What information does it store? So the answer is process control block is a data structure maintained by the operating system for each process. It serves as the repository of information about a process, and there are several categories of information that can be stored in process control block. For example, process ID can be stored in the process control block. Process ID is a unique identifier that identifies the process. Then the state of the process, in which state the process is in, can also be stored as a information in the process control block. For example, the process can be in any one of these states: new state, ready, running, waiting, or terminated. The information about the program counter can also be stored in the process control block, and program counter contains the address of the next instruction to be executed. The next type of information that can be stored in process control block is about the CPU registers. That is, all the contents of all process-centric registers can be stored as information in the process control block. CPU scheduling information can also be stored in the process control block, and scheduling information pertains to information about priority of the process and scheduling queue pointers. Memory management information can also be stored as a part of information that can be stored in process control block. And memory management information, that is information about the page tables, limits of memory limits, segment tables. Accounting information can also be stored in process control block, that is how much CPU has been used by a particular process, time limits, and what are the process numbers. Input output status information can also be stored in the list of, in the process control block, and input output status information comprises of list of input output devices allocated and the files which are open currently. Second question is, define threads. Why is multithreading useful in modern computing, modern systems? Thread is the smallest unit of execution within a process. It is sometimes called a lightweight process. And why multithreading is useful? First fact that why the multithreading is useful is the responsiveness. In interactive applications, multithreading allows the program to continue running even if the part of the program is blocked. So the entire program does not fail and it remains responsive. Second reason why multithreading is useful is resource sharing. That is, threads share the memory and resources of the process they belong to, enabling efficient communication. Third reason why multithreading is useful is the economy part. That is, creating and context switching threads is much cheaper than the process creation and context switching of processes. Next is scalability. Programs can take advantage of multiprocessor architecture by running threads in parallel. And the last benefit can be better CPU utilization. While one thread waits for input output, other threads can execute. Example of multithreading can be, for example, a web browser can use one thread for user interface, another thread can be used for downloading, another thread can be used for rendering. That's why multithreading is useful. Third question is, explain the layered approach in operating system design. Give one advantage of using this structure. So the layered approach divides the operating system into several layers, that is levels, and each layer is built on the top of lower layers. The bottom layer, that is the layer 0, is the layer about hardware, and the highest layer, that is the topmost layer, layer N, is the user interface, represents the user interface. So the topmost layer N is user interface, then comes underneath comes the user programs layer, then input output management, and the second layer from last is memory management layer, and the bottommost layer is the hardware layer. Advantage is modularity and debugging. Each layer uses functions and services of only lower level layers. This simplifies debugging and system verification. If an error is found during debugging of a particular layer, the error must be on that layer because the layers below it are already debugged. Next question is list three functions provided by an operating system and explain any one of them briefly. There are three functions which can be performed by the or provided by the operating system are process management, second is the memory management, and third is file system management. As a part of the answer, we would like to explain the process management as one of the functions provided by the operating system. Process management involves creating, scheduling, and terminating processes. The operating system must create and delete both user and system processes, suspend and resume processes, provide mechanisms for process synchronization, provide mechanisms for process communication, provide mechanisms for deadlock handling. The operating system maintains the process control block for each process, allocates CPU time using scheduling algorithms, and ensures proper execution and termination. The next question is explain the different types of schedulers in an operating system. What is meant by multiprocessor scheduling? Types of schedulers are first scheduler is the long-term scheduler or also known as job scheduler. It selects which processes should be brought into the ready queue, also controls the degree of multiprogramming, executes less frequently, that is, it executes after seconds or after minutes. Second is short-term scheduler, that is also known as CPU scheduler. CPU scheduler or short-term scheduler selects which process should be executed next from the ready queue, and it executes very frequently, that is, after few milliseconds, the short-term scheduler executes, and it must be very fast. Third is the medium-term scheduler. It is responsible for swapping processes in and out of memory. It helps in reducing the degree of multiprogramming and also performs swapping. Multiprocessor scheduling involves assigning processes to multiple CPUs. Key considerations are load balancing, that is distributing processes evenly across all the processors. Processor affinity, that is keeping a process on the same processor to benefit from cache memory. Symmetric versus asymmetric. In symmetric, each processor is self-scheduling. In asymmetric, one processor, that is the master processor, schedules for all the remaining. Next question is the consider these processes P1, P2, P3, P4, of which we are given arrival time, burst time, and the priority. We have to apply the non-preemptive priority scheduling and compute the average turnaround time. So the burst time is the time which is taken by the process to execute. Arrival time is the time at which the process arrives for execution, and priority has been given to us. We have to apply the non-preemptive priority scheduling. So let us carefully go through the work through the non-preemptive priority scheduling for the given processes. So as I have said, this information has been given to us. For process P1, arrival time 0, burst time 6, priority 3. Process P2, arrival time 1, burst time 4, and priority is 1. Similarly, P3, arrival time 2, burst time 5, priority 2. P4, arrival time 4, burst time 5, priority 2. When we are not given that whether the lower priority number is the higher priority or the higher priority number is the higher priority, so in that we have to take an assumption. We by convention we need to consider the lower priority number as the higher priority. For example, process P2 is having priority 1, so it is the lower number. Lower number, it means P2 has the highest priority, so CPU will be allocated to P2 first. So this is the scheduling order. At time 0 only, as you can see, P1 process arrive at time 0. So at time 0 only P1 has arrived. So we have to start the execution of P1. P1 runs till completion because this is the non-preemptive priority scheduling algorithm, CPU scheduling algorithm. So we have to run the process till completion because it is non-preemptive. So it will finish at time 6 because burst time for process uh, P1 is 6. As you can see, the priority P2 is having higher priority, but at arrival time 0, the P2 does not arrive. P2 arrive at arrival time 1. That's why, first of all, P1 is executed, right? So after that, at time 6, P2, because P2 has arrived at arrival time 1, so at time 6, obviously it will arrive. It has already arrived, and then uh, P3 arrives at arrival time 2, P4 arrives at arrival time 4, and are all waiting. Among them, P2 has the highest priority, as I have said. Priority of P2 process is 1, therefore it is having high priority. Out of P2, P3, P4, P2 will run first, that is P2 run next, and it will finish at time 10 because the burst time is 4. 6 plus 4 is 10. That's it will also run to completion because it is a non-preemptive priority scheduling algorithm. So after 10, at time 10, remaining processes have arrived. Both of the processes P3 and P4 have the same priority too. So there is a tie. In that case, we have to choose that process that have arrived first. For example, that's why the P3 has arrived first. That's why the P3 process will run. And the burst time of P3 is 5, as you can see here, and therefore it will finish execution at time 15. At time 15, only P4 process is remaining, and P4 will run, and it's also having burst time of 5. So 15 plus 25, 15 plus 5, 20. That is the process P4 will also finish at time 20. So the execution order is P1, P2, P3, P4. Now we have to compute the completion time, turnaround time, and waiting time. Completion time, as the term itself speaks, as the term signifies, completion time is the time at which the process is completed. Process has completed its execution. Turnaround time is the formula is for turnaround time, computing turnaround time. We have the formula that is completion time minus arrival time. Waiting time formula is turnaround time minus burst time. So you can compute all this. P1 completion time is 6. So the turnaround time, as I have said, turnaround time is completion time minus arrival time. So for P1, completion time is 6, arrival is 0. So 6 minus 0, 6. Waiting time is turnaround time minus burst time. So turnaround time is 6 and 6 is the waiting time. Sorry, waiting time is turnaround time minus burst time. So for process P1, turnaround time has to be computed as 6 and the burst time is also 6. So waiting time will be 6 minus 6, 0. So you can compute the completion time, turnaround, waiting time for the remaining process on your own, at your own, right? So we have successfully computed uh, all these three times: completion, turnaround time, and waiting time. But in the question, we have been asked to compute the average turnaround time. So average you already know, because we are having four processes. We are having four processes. We have to sum up all the turnaround time, that is 6 plus 9, 6 plus 9 plus 13, 28, 28 and 16. 44, 44 divided by 4, that is 11 units. That is the average turnaround time, right? Gantt chart you can also easily draw, as the sequence of process execution is P1, P2, P3, P4. So P1 will P1 has burst time of 6, P2 has burst time of 4, P3 has burst time of 5, P4 has also burst time of 5. So you can draw the Gantt chart as well. Clear? So the turnaround time have has already been computed by us previously, which will come out as 11. Right? Next question is question number 7. Question number 7. So question number 7 says apply the round robin scheduling. Time quantum has been given to us as 3. Again, we are having three processes. Arrival time and burst time has been given to us. We have to draw the Gantt chart and calculate the average waiting time. You know, waiting time formula is turnaround time minus burst time. So we have to compute first the turnaround time. Only then you will be able to compute the waiting time, right? So first of all, we can draw the Gantt chart. Arrival P1 arrives first. So that's why uh, P1 will execute for what time quantum, for 3. However, the bus time is 6, but it will not run for the entire 6 units of bus time, because time quantum has been given to us as 3. So this is the Gantt chart, as you can see here. So this is the scheduling order. I will also be showing you the Gantt chart. So time 0 to 3, P1 will run. Time 3 to 6, because time quantum is 3 fixed. So from time 3 to 6, P2 run. 6 to 9, P3 run. Then the remaining time will be executed. So the bus time of P1 is 6. It has already executed its execution for 3 units. So now P1 will again run for 3 units. That is from 9 to 12. And then P2 remaining 2, that is 12 to 14, and P3 has already completed its entire 3 units of burst time, right? So we can also draw the Gantt chart in this manner. And this is the Gantt chart. It shows that P1 arrives at time 0 and up to 3, the P1 completes its execution, but it is remaining 3 units of execution of P1 is remaining that will be allocated after once the P2 and P3 are executed. So P2 will execute up to time unit 6, P3 will be executing up to time unit 9, then remaining of P1, that is remaining 3 units of P1 will be executed. Will P1 will get its execution completed up to 12 units of time, and the remaining 2 units, as you can see here, P2 is having burst time of 5. Earlier it has been executed for 3, so remaining burst time is 2. So that's why 12 plus 2. P2 will complete its execution up to 14 units of time. So we can we can compute the completion time now, because we have to compute the average waiting time. Waiting time formula is turnaround time minus burst time. So we have to compute the first of all we have to compute the turnaround time. For turnaround time we need the completion time. So that's why we have to firstly compute the completion time. So as you can see here, P1 will complete its execution at 12 units of time. P2 will complete its execution at 14 units of time. P3 will finish its execution at 9 units of time. So easily you can compute the turnaround time. As I earlier said, the formula for computing turnaround time is completion time minus arrival time. So P1 completion time is 12, arrival is 0. So turnaround time is 12. For process P2, the completion time is 14 and the arrival time is 1. So for 13 is the turnaround time for P2. P3, the completion time is 9 and 2 is the arrival time. So 7 will be the turnaround time for process P3. Now we can easily compute the waiting time. As I have earlier told you, the formula for computing waiting time is turnaround time minus burst time. So all the values have been given to us. Now we can easily compute the waiting time, and then we sum up and then divide by 3. We can compute the average waiting time. So that's why the average waiting time will be 6 units. 6 plus 8 plus 4, 18. 18 divided by 3, that is 6 units. Okay. So this is you can also draw the Gantt chart. So if you want to draw this Gantt chart, you have to follow this scheduling order strictly, as I have earlier told you. This scheduling order. This scheduling order. However, we have drawn the Gantt chart here. Again, the Gantt chart had been drawn for your convenience again. So you can see here. Okay. Again, the waiting time has been computed for your convenience. That is earlier computed to be 6 units. Okay. This step has been repeated. That is Gantt chart and waiting time has been computed repeatedly here. So please ignore this. Okay. Now the next question is question number 8. Question number 8 says that what is meant by an operating system, and mention any 2 key tasks that are performed by the operating system, right? So the answer to this question is operating system is a system software. So you have to remember this. Operating system is a system software. Operating system is a system software that manages the hardware, software resources, and provides the common services for all the computer programs. It also acts as an intermediary between users and the computer hardware. The 2 key tasks are performed by the operating system are resource management. The operating system manages CPU, memory, disk space, input-output devices, allocating them efficiently among the competing processes. So all these resources are allocated among the competing processes by the operating system. That is CPU, memory, disk space, input-output devices. All these are the resources that are allocated to competing processes by the operating system. So this is the first task of the operating system, that is the resource management. Second task is the user interface. So as you already know, operating system provides an interface that can be command line interface also, or you can GUI, that is graphical user interface also. So operating system provides an interface through which users can interact with the computer system and execute programs. Okay. Now we jump to the next question, that is question number 9. Describe a time sharing operating system. How does it differ from a multitasking system? So, time sharing operating system allows multiple users to share computer resources simultaneously. CPU time is divided into time slices and allocated to different users or processes in rotation. Characteristics of a time sharing operating systems are multiple users can access the system simultaneously. Each user gets a time slice, that is time quantum. as we have already seen in round robin CPU scheduling algorithm, also provides illusion of dedicated system to each user. So although multiple users are sharing a system, but has each user is in illusion that he or she is assessing a system dedicated to her or him. But multiple users are using that system simultaneously. That's why the time sharing operating system. Examples of time sharing operating systems are Unix and Linux operating system. Now, how does it differ from multitasking system? So these are some of the differences between time sharing operating system and multitasking system. First aspect we will be differentiating between time sharing and multitasking is about the focus. Time sharing operating system in time sharing operating system, multiple users are sharing resources, while in multitasking system, multiple tasks or processes are running. As far as the aspect of primary goal is concerned, the primary goal of time sharing operating system is to ensure the fair CPU distribution among users, whereas the multitasking has to ensure the efficient task execution. Third aspect on which we can differentiate between these two is the time quantum. So the concept of time quantum is strictly enforced in time sharing operating system, but time quantum concept may vary by priority in multitasking system. As far as context is concerned, time sharing operating system is a multi-user environment, whereas multitasking system can be single or multi-user as well. So time sharing operating system is a type of multitasking specifically designed for multiple users. The next question, that is question number 10, is what do you understand by real-time operating system? Explain the difference between hard and soft real-time systems. So the definition of real-time operating system is real-time operating system is designed to process data and events within strict time constraints. So there are two types of real-time system, that is hard and soft. First is hard real-time system in which deadlines are absolute. Missing a deadline is a total system failure. There is no place for tolerance for delays in hard real-time systems. Examples are air traffic control, in which there is missing a deadline is a total system failure and tolerance is not allowed. Tolerance for delays is not allowed. Another example is medical systems, that is the pacemakers, industrial control systems. And what are the consequences of missing deadline in hard real-time system? It results in catastrophic failure. It can also result in loss of life. Whereas second is the soft real-time system. In this case, deadlines are important but not so critical, unlike in hard real-time systems. Missing occasional deadlines is tolerable in real-time soft real-time systems. It can cause, however, performance degradation. Examples are video streaming, online gaming, multimedia systems. And the consequences of missing deadline in soft real-time systems are that is the quality of service is reduced. Only the quality of service is reduced, there is no loss of life. So the key difference between these two is in hard real-time systems, correctness depends on both logical result and time. In soft real-time systems, time is important for quality but not for correctness. The next question is about the define the turnaround time, waiting time, and response time. Why might a system show high CPU usage but still have poor response time? We have already computed all these. So you know what is turnaround time? That is the total time from process submission to completion. That is the formula for turnaround time is completion time minus arrival time. Because process submission means arrival time. Process submission means arrival time. So when the process completes, completion time minus arrival time is the turnaround time. Waiting time is the total time a process spends in the ready queue. So waiting time formula is turnaround time minus burst time. Clear? And then comes the response time. That is the time from submission until first response is produced. So response time formula is time of first execution minus arrival time. So high CPU usage with poor response time. This can occur due to poor scheduling algorithm. For example, if you are using first come first served CPU scheduling algorithm with long processes, it can make short processes wait. So short processes can wait for a long time when you are using the first served CPU scheduling algorithm, and it results in high CPU usage with poor response time. High CPU usage with poor response time can also occur due to the high context switching overhead. That is too frequent switching, that is waste CPU cycles. Third, it can also occur due to the priority inversion. that is high priority processes waiting for lower priority ones. Input-output bound processes can also be one of the reason of high CPU usage with poor response time. That is CPU busy but not serving interactive requests quickly. Then high CPU usage with poor response time can also occur due to starvation. That is starvation is some processes monopolizing CPU while other processes are waiting indefinitely. So example is a batch processing system running long CPU intensive tasks shows 100% CPU usage, but interactive user request must wait, resulting in poor response time. This is the example. Next question is explain the concept of process memory layout. How do different schedulers help in maintaining system efficiency? So process memory layout. Process memory is divided into sections. These sections are stack. Stack will always grow downward. That is, stack will store local variable and function calls, whereas heap will grow upward and heap contains dynamic. He provides the dynamic memory allocation. Some part is uninitialized. That is the some global and static variables are uninitialized. Then comes the initialized portion. That is where the globals and static variables are initialized. Then comes the text, that is the program code. So how schedulers maintain efficiency? First is you by CPU utilization. Keep CPU busy by quickly switching between processes. Next is throughput, that is by maximizing the number of processes completed per unit time. Next is schedulers also maintain efficiency through balanced load, that is through the mix of CPU bound and input output bound processes. By fair allocation, that is preventing starvation through fair time distribution. Response time optimization, that is by prioritizing interactive processes for better user experience. By resource management, that is by coordinating with memory manager for optimal performance. The next question is question number 13, that is what is multi-threading? Compare user level threads and kernel level threads. Which performs better under heavy workload? So multi-threading is the ability of a program to execute multiple threads concurrently within a single process. Now we'll be comparing user level threads with kernel level threads. First of all, we can differentiate between user level and kernel level thread in from the aspect of management. So user level threads are managed by user level library, whereas kernel level threads are managed by the operating system kernel. As far as context switch is concerned, context switching occurs in user level threads at a faster pace because there is no involvement of kernel, whereas context switching happens very slowly in kernel level threads because of kernel mode switch. As far as blocking is concerned, if one thread blocks, all threads will. If one user level thread blocks, all user level threads will block. Whereas uh, in kernel level threads, individual kernel threads can block. As far as multiprocessor is concerned, user level threads cannot utilize multiple CPUs, whereas kernel level threads can run on different CPUs. As far as creation is concerned, user level threads can be created at a faster and cheaper rate, whereas kernel level threads are slower and it results in greater overhead. As far as portability is concerned, user level threads are more portable. They can be ported from one operating system to another, whereas kernel level threads are operating system dependent. They are less portable, or entirely they are not portable. Examples of user level threads are POSIX P threads, and whereas examples of kernel level threads are Windows threads or Linux threads. Now the performance under heavy workload. Kernel level threads perform better under heavy workload in contrast to user level threads because reason is kernel level threads can truly run in parallel on multiple CPUs. If one kernel level thread is blocked, it does not block other kernel level threads. Kernel level threads also result in better system integration. Operating system can make better scheduling decisions using kernel level threads. User level threads may be faster for lightweight non-blocking operations, but user level threads fail to scale under heavy workload. Next question is about the multi-threading models. That is, describe different multi-threading models, compare their strengths and weaknesses, and suggest the most suitable one. So there are three main models. First one is the many-to-one model, that is where the many user threads map to one kernel thread. Strengths of many to one model are efficient thread management, fast context switching. Weaknesses of many to one model are entire process blocks if one thread makes blocking call. Cannot run in parallel on multiprocessor. Examples are green threads in older Java. Second model is one-to-one model where each user thread is mapped to one kernel thread. Strengths of one-to-one model are true parallelism on multiprocessors. One thread blocking does not affect others. It results in better concurrency. Weaknesses of one-to-one model are overhead of kernel thread creation, limited by system's kernel thread limit. Examples are Windows and Linux. And the third is the many-to-many model, where many user threads multiplexed onto smaller or equal number of kernel threads. Strengths are it combines benefits of both models. Developers can create many threads. Kernel threads can run in parallel. It is very flexible. Weaknesses of many-to-many model are it is complex to implement, more difficult to program. Example is the Solaris. Most suitable model is the one-to-one model. That is, one-to-one model is most suitable for modern systems because modern systems have efficient kernel thread management. True parallelism is crucial for performance, better system integration, and is also widely supported. Next question is the question number 15. That is, what is batch operating system? Mention its advantages and disadvantages. Batch operating system processes jobs in batches without user interaction. Jobs with similar requirements are grouped and executed together. The characteristics of batch operating systems are jobs are collected and processed in groups. There is no direct user interaction during execution. Jobs are submitted via punch cards or job files. Execution is supervised by the operator. Advantages of batch operating systems are efficiency, that is reduced idle CPU time by batching similar jobs. Automatic job sequencing, there is no manual intervention needed between jobs. Resource utilization, better use of expensive computer time. Suitable for repetitive tasks. Batch operating systems are suitable for payroll, billing, report generation. Disadvantages are no interaction. Users cannot interact with executing jobs. Turnaround time, long wait time to get results. Debugging difficulty, hard to debug programs. CPU starvation. Short jobs may wait for long jobs to complete. And no priority, all jobs are treated similarly. Now we jump to question number 16. These two questions will be discussed at the end of the session. These two questions will be discussed at the end of the session. So the next question is question number 16. Given processes P1, P2, P3, again arrival time, burst time has been given to us. We have to use first come first serve CPU scheduling to draw the Gantt chart and calculate average waiting time and turnaround time. So this is very simple for us. We have also solved such types of problems in past also. So let us see the answer to question number 16. So first come first served CPU scheduling algorithm executes processes in order of arrival. So the process which arrives first will be executed first. That is the burst time through the given units of burst time. So Gantt chart can be like this. P1 arrives at time 0. So P1 arrives first. So burst time is 5. So P1 will be executed up to time unit 5. Then P2 arrive at 1 because we have reached up to 5 units of time. So P2 has already arrived at arrival time of 1. Then P2 will complete its execution up to 8 units of time because of burst time is 3. That is 5 plus 3 is 8. Then P3 will be executed because it arrives at arrival time is 3 and 8 plus burst time is 4. So 8 plus 4, 12. So P3 will get its execution completed at 12 units of time. Now we can easily compute the this arrival time is known to us. Burst time also given to us. Completion time we can already see from here. P1 completion time is 5. P2 completion time is 8. P3 completion time is 12. Right. So turnaround time formula we already know, that is completion time minus arrival time. Both of completion time is also known to us. Arrival time is also known to us. So we can compute the turnaround time. Then waiting time is turnaround time minus burst time. So turnaround time we have just computed, and we can compute the waiting time by subtracting burst time from turnaround time. So once we compute the turnaround time and waiting time for each of the processes, then we can compute the average. That is by taking their sum and divide by total number of processes. Right. So this is the answer to the given problem. Now we could jump to question number 17. Question number 17 says that again we are given some processes, three processes are given, their arrival time and burst time are given. Now we have to apply non-preemptive. Always remember that non-preemptive scheduling algorithm is the shortest job first, that is the SJF, shortest job first scheduling algorithm. And the preemptive version of this is known as the SRTF, that is shortest remaining time first CPU scheduling algorithm. So in this case, we have to apply non-preemptive shorter job first. Again, we have to compute average waiting time, turnaround time, and CPU utilization. So it is very simple for us. So this is the timeline construction. So the process P1 arrives at 0, P2 at 3, and P3 also arrived at 3. But uh, P1 will execute first for a burst time of 4 because it has arrived at time arrival 0. Now we have reached up to time 4. At that time, the P2 has arrived because P2 has arrived at, sorry, question number 70. So P2 has arrived at time arrival time of 3. So up to 4, P2 has arrived. But you can see at 3 arrival time, P3 has also arrived. And burst time of P2 is 5, burst time of P3 is 2. So because the burst time of P3 is lesser than the burst time of P2, P3 will be executed first and P2 will be executed after P3. Clear? So P3 will be executed first. So P3 will complete its execution 6 plus 4 plus 2 up to 6, and then 6 plus 5 11. 11 up to 11 time units P2 will complete its execution. So you can easily draw its Gantt chart and you can compute the given required parameter, that is you can easily compute the average waiting time, turnaround time, right? So you know already for computing the turnaround time we need the completion time because the formula for turnaround time is completion time minus arrival time. So the P1 completes at 4. As you can see here, P1 completes at 4. Completion time is 4. P1 is 4. Then P3. P3 completes at time 6. Completion time for P3 is 6. P2 completes at 11. Right? So turnaround time can be easily computed by subtracting the completion by subtracting the arrival time from the completion time. Arrival time is already given to us. Arrival time is already, this is arrival time of each of the processes P1, P2, P3 has already given to us. So we can easily compute the turnaround time, that is subtracting the arrival time from completion time. Then we can compute the waiting time. Waiting time formula is turnaround time minus burst time. Burst time is given to us and turnaround time we have already computed here, right? So we can compute the average of them by summing them and by divided by 3, right? Now, one more thing we have been asked, that is what is the CPU utilization? So CPU utilization will be 100%. Why? Because total time span is 0 to 11 unit. All the three processes P1, P2, P3 have been executed up to 11 units, and total busy time is also burst time. That is burst time. You can see here burst time is 4, 2, and 5. That is also 4 plus 2 plus 5 is also 11. So CPU is busy for the whole 11 units, and total time is also 11 units. So 11 divided by 11 into 100, CPU utilization comes out to be 100%, right? So this is the Gantt chart drawn. You can see here P3 has been executed ahead of P2. Why? Because burst time of P3 is 2, which is lesser than the burst time of 5 of P2, right? So you can draw the Gantt chart as well. Clear? The for your convenience, the waiting time and turnaround time, and hence for the average and waiting and average turnaround time and chip utilization has been computed again for your convenience. You can refer to this Gantt chart, right? This is the Gantt chart, and you can easily compute all these quantities. So we are done with the solution to the problem number 17. Now we come to question number 18. Question number 18. Again, we are given processes P1, P2, P3, P4. Arrival time, burst time has again been given to us. Now, earlier in the previous question, I have told you SRTF is shortest remaining time first. That is the preemptive. Preemptive. Preemptive means that we have to preempt the process first. If there is another process which is having less burst time, then the earlier process being executed will be preempted. CPU will be taken away from that process, and if any other process is having shortest remaining burst time, then that will be given a chance to for execution by the CPU, right? So that is the preemptive version, SRTF. So, as you can see here, these are the arrival time given to us. Burst time has also been given to us. Now see here, what is the difference between SJF and SRTF? SJF is shorter job scheduling, shorter job first scheduling, that is the non-preemptive. Whereas SRTF is the shortest remaining time first, that is the preemptive. So as you can see here, at time 0, P1 arrives, right? So P1 will run for only 1 unit because at arrival time 1, burst time of remaining burst time of so the as you can see here, at arrival time 0, P1 arrives, right? So P1 will execute only for one burst time, 1 unit of burst time. Remaining, why? Because at arrival time 1, P2 arrives and burst time of P2 is 3. So the remaining burst time of P1 is 6 because P1 has executed for only 1 unit of burst time. So the remaining burst time of P1 is 6, whereas the at arrival time 1 P2 arrives and the burst time of P2 is 3. So because the burst time 3 of process P2 is lesser than remaining burst time of P1, that is 6. So P2 will be given a chance for execution by the CPU, right? So P2 will arrive, and after that, that is P1 will be now preempted. That's why it is known as preemptive. SRTF, shortest remaining time for scheduling, that is the version of preemptive version of CPU scheduling algorithm. So that's why P1 will be preemptive. CPU will be taken away from P1 and given to P2. So P2 will now again run for only P2 will now run again for only what? P2 will be run for 2 units. Just a minute. Remaining is 2. So P2 will run for 1 unit of time, right? So at time 2, yes. So after P2 will run for 1 unit of time. Remaining bus time of P2 will be 2, and at 2 arrival time, bus time of P3 is 5. So P2 cannot be preempted. So P2 will run for up to 2 units of bus time. So that I can show you the Gantt chart. So P2 will run for P1 is run for 1 unit of time. So P2 will run for P2 bus time is 3. So at arrival time 1, okay. Uh, okay. So P2 will run for 2 units of bus time, right? That is from 1 to 3. But when it is executed for 2 units of bus time, the process 1 plus 2, 3. So at arrival time 3, P4 arrived, but the remaining bus time of P2 is what? 1, and bus time of P4 is 2. So P2 will not be preempted because remaining bus time of P2 is 1, which is less than the bus time of P3 or P4. So P2 will run entirely for 3 units of bus time, as you can see in the Gantt chart. So P2 will run for entire bus time of 3 units. That is, P2 will complete its execution at time unit 4. So I hope you have understood the concept of preemptive scheduling. And that is, we have to see the remaining time, shortest remaining time first. Uh, right? So this is the Gantt corresponding Gantt chart, and remaining formulas for computing the waiting time will remain same. First of all, you have to compute the completion time for each of the processes, then turnaround time, then waiting time, then you have to take the average. Right? So this is the solution. Now we come to next question, that is the to question number 21. See here. Now, two processes operate on x is equal to 6. So value of x is given to as 6. There are two processes which are operating on this value of x, that is 6. List all possible outcomes of x. So we have to compute all possible values of x, and we also need to identify the problem, and we have to explain the problem. Right? Now, so in this question, basically we are having the race condition because both of the processes P1 and P2 are operating on the same variable x, right? So there is a race between these processes P1 and P2 for accessing the value of x, right? That's why the race condition problem. It is known as race condition problem. Possible outcomes can be, for example, each operation involves three sub operations. First is read operation, then modify operation, then write operation. So the first scenario is P1 completes, then P2. So P1 will first read the value of x, that is 6, right? And then it will compute P1, that is 6 plus 2, 8, right? So it will compute 8. We have modified the value of x. P1 has modified the value of x. Then we have the write operation. Then the value 8 is written, right? Then because the value 8 has been written, that's why now P2 will read the value of x as 8, not 6. Please see here, the value of x will not be read as 6 because the 8 value has been written by process P1. That's why P2 will read the value of x as 8 and not 6. P2 will read the value of x as 8 and not 6, right? So P2 will read the value of x as 8. So 8 minus 4 is 4. So it will compute the value of x as 4, that is 8 minus 4 is 4, and then it will write the value as 4. Result will be 4. This is the final value that has been written by process P2. So we have to compute all the possible scenarios. So the first scenario gives the value of x as 4. Now scenario 2, what can happen in scenario 2? In scenario 2, first P2 can complete, then P1. In the scenario 1, P1 was executing first. In scenario 2, P2 is executing first. So P2 will read the value of x as 6. So because the initial value is 6. So 6 minus 4 is 2. So computed value is 2. Now the P2 has written the value of x as 2. So P1 will read the value of x as 2 now, not 4, not 6. P1 now read the value of x as 2 and not 6. So 2 plus 2 will be 4. So the value of x computed by P1 is 4 and 4 will be written. So in this case also, the value of x has been computed as 4 when P2 first execute, then P1, right? Scenario 3 can be interleaved, that is interleaving. First P1 read, then P1 does not compute the value of x. After reading the value of x by P1, the same value is read by P2. Then P1 write and then P2 write. See, clear? So initial value of x is 6. So P1 as well as P2, both of them will read the value of x as 6, right? Then P1 write. For writing operation, P1 has to compute the value of x through this equation P1. So 6 plus 2, 8. So it will write the value of x as 8. Now P2, because P2 has also read the value as 6. So 6 minus 4, that is 2. So the final value that has been written by process P2 of x is 2. So the final value of x is 2 in this case, not 8. Because the latest value of x is 2 here. Right? So this is the scenario 3. Now, in scenario 3, P1 was first reading. But in scenario 4, P2 is first reading, then P1 reading, and then P2 writing, and then P1 writing. As you can see in scenario 3, P1 was writing first and then P2 was writing. But in scenario 4, P2 is writing first and then P1 is writing. Right? So both P2 and P1 will read the value of x as 6. P2 will compute 6 minus 4 is 2. Uh, P2 will 6 minus 4 is 2. So 2 is written. Then P1 uh, P1. So the value of x is 2. So P1 just a minute. Yes, because the value of x read by the P1 is 6. So 6 plus 2 is 8. So the final value of x is 8 in this scenario number 4. So all the possible outcomes are x can comprise of values 2, 4, and 8. We have seen in scenario 1 and 2, the value of x was 4. In scenario 3 and 4, the value of x has come out to be 2 and 8 respectively. So this is the problem identified, as I've earlier told you. This is known as race condition problem, where both of processes P1 and P2 are in the race of accessing the value of x and computing the value of x and reading and writing the value of x. Right? So multiple processes accessing shared data concurrently. Final result depend on the timing and order of execution. As you can see, different order of execution and the value of x has come out to be different in each case. So non-deterministic behavior is also the sign of race condition problem. The solution to this race condition problem can be we need to use the mutual exclusion through the concept of loops and semaphore to ensure the atomic operations. Right? So this is the solution to the race condition problem. Then we come to question number 22. Consider the following code. Consider the following code. While flag J, flag I is equal to true, critical section, flag I equal to false. Check whether this ensures mutual exclusion. Explain your reasoning. First of all, you should know the mutual exclusion. Mutual exclusion means only one process can enter and execute in its critical section. Simultaneously, no other process can enter in its critical section or can execute the critical section. Only one process should be in the critical section, should enter in the critical section. So now see. Let us carefully analyze this code which has been given to us. See, so each process I has a flag. Each process I has a flag, that is flag I, indicating whether it wants to enter the critical section. Before entering, process I waits while flag J is true. So if flag J is true, process I has to wait because flag J is true, meaning that the process J is already inside or wants to enter in its critical section. So process I should wait. So then it sets its own flag to true. So after that, after the uh, process J has completed its execution in its critical section, then only process I can set its own flag to true, and then process I will enter the critical section and reset its flag to false afterward. Clear? So problem with ordering. So notice the sequence. The process first checks while flag J. So and only afterwards sets the flag I equal to true. As you can see here, this condition is being the process first checks this while condition, and only after that we are setting the value of flag I as true. But this means that there is a race condition. Suppose both processes P0 and P1 execute flag J simultaneously. So at that moment, both see flag J equal to false since neither has set its flag yet. So both exit the while loop and set their own flag I equal to true. So process I will also set its flag to true. Process J will also set its flag to true. So both processes will enter the critical section at the same time. So that violates the mutual exclusion. So there is a violation of mutual exclusion. That is, mutual exclusion requires that only one process can be in the critical section at a time. In this algorithm, it is possible for both processes to enter simultaneously if they check the other's flag before either sets its own. So therefore, mutual exclusion is not guaranteed. So the correct approach is to ensure mutual exclusion. The process should set its own flag before checking the other flag. So the code should be like this. That is the Peterson algorithm is the solution to this problem. The flag should be first set by the process I and turn equal to j means the process j has the turn to enter its critical section. Then we are having while condition flag j and turn is equal to j. So only if the flag j is true and it is also the turn of the process j will enter its critical section. So once the process j completed its execution in critical section, so flag I equal to false, it means that the process has completed its execution in critical section. So this ordering prevents both processes from slipping through at the same time. So the given code does not ensure mutual exclusion because both processes can simultaneously pass the while flag j and check before setting their own flags, leading to concurrent entry into the critical section. Solution to this problem I have earlier told you is the Peterson algorithm. That is the next question. That is explain how Peterson algorithm ensures mutual exclusion between two processes. What happens if both try to enter the critical section at the same time? So Peterson algorithm is a classical software solution for mutual exclusion between two processes. Let us break it down. The algorithm says that the for two processes P0 and P1, we use flag I indicates if process I wants to enter the critical section. Turn means it indicates whose turn it is to enter. So process I executes flag I equal to true, meaning that process I want to enter into the critical section. Turn is equal to J means let the other process go first if it wants. Then we are having this while condition and flag I equal to false means that process I is saying that I am done. Process this statement is saying that process I has executed in its critical section. Process I has finished executing in its critical section. So why the Peterson algorithm ensures mutual exclusion? Both must set their flag. A process cannot enter unless it sets flag I equal to true. Turn variable resolves conflict. If both processes set their flags at the same time, the turn variable decides who waits. Suppose P0 sets turn equal to 1 and P1 sets turn equal to 0. Then P0 will wait if flag 1 is true and turn equal to 1. Simultaneously, P1 will wait if flag 0 is true and turn equal to 0. So as you can see here, uh, suppose P0 sets turn equal to 1. So it means that it is turn of process P1 and P1 sets turn equal to 0. So it means P0 is saying it is turn of P1. P1 is saying it is turn of P0. So that's why both processes cannot enter their critical section simultaneously. So in this manner, mutual exclusion is guaranteed. So P0 will wait if flag 1 is true. Flag 1 is true means process P1 wants to enter or already is inside the critical section. So in that case, P0 has to wait because P1 is in its critical section or wants to enter in critical section. And also turn equal to 1 is also. These two conditions should be true to enter P1 into the critical section. So flag 1 is true means process P1 is already inside its critical section or wants to enter in its critical section. And turn equal to 1 is also means that it is the turn of process P1 to enter into its critical section. So P0 will wait. Simultaneously, P1 will wait if flag 0 is true and turn equal to 0. Right? So this is the vice versa what I have told you in this line. Right? So only one of these conditions, the one condition is this, one condition is this, and second condition is this. So out of these two conditions, only one can hold at a particular time. So only one process proceeds while other waits. Proceed means only one process can enter it into its critical section and execute its critical section, right? So the mutual exclusion property is guaranteed here. That is using the Peterson algorithm. No simultaneous entry. As I earlier told you, this while condition both cannot pass the loop together. So at least one process will be forced to wait, ensuring mutual exclusion. If both try to enter at the same time, both will set their flag to true, both set turn to other processes. The last assignment to turn determines whose turn it is. The process whose turn it is waits while other enters the critical section. Thus, even in simultaneous attempts, only one process can enter into its critical section and the mutual exclusion is preserved. Right? So the conclusion is Peterson algorithm guarantees mutual exclusion by combining flags and a turn variable to break the ties. If both processes try to enter at the same time, the turn variable ensures that one waits while the other proceeds to enter into critical section and executes in critical section, preventing the concurrent entry. Now we jump to question number 24. Write a solution using semaphores for the producer consumer problem and explain the purpose of each semaphore used. So here is a clean semaphore based solution to the producer consumer problem along with an explanation of each semaphore role. So the problem setup, we have a bounded buffer that is a shared queue of size n. So we have a buffer. The size of the buffer is capital N. Multiple producer. Producer consumer problem means producer want to produce and consumer want to consume some item. Producer will produce an item, consumer will consume an item. So multiple producer generating item, that is producing items and placing them into the buffer. So producer will producer is generating or adding the item into the buffer, right? And consumer will consume that item or remove that item from the buffer, right? This is the problem. Now the semaphore used for this producer consumer problem are, first semaphore is the empty semaphore. So as the term itself speaks, as the term signifies, empty means it will count the number of empty slots in the buffer. That is how many empty slots are there in the buffer, which can be produced by the producer. So this empty buffer, sorry, the empty semaphore is initialized to capital N. That is, capital N is the size of the buffer. And empty semaphore also ensures producers don't overfill the buffer because the size of the empty buffer is n. Only n items can be added into the buffer. So producers cannot overfill the buffer. Second semaphore is the full semaphore. That is, as the term signifies, it full semaphore counts the number of filled slots. That is the how many number of slots are filled. So the full semaphore is initialized to 0. It means that the number of filled slots in the buffer are already 0. So it ensures that consumer don't try to consume from an empty buffer. So if the buffer is empty, consumer cannot consume because there is nothing in the buffer, right? Next semaphore is the mutex semaphore. This is a binary semaphore, that is value is 0 or 1, or it can also be set to be as a lock to ensure the mutual exclusion. So with the help of this semaphore, mutex semaphore, mutual exclusion property is ensured or enforced when accessing the buffer. And this mutex semaphore, value of this mutex semaphore is initialized to 1. Then it will become 0, then 1, then 1, 0, 1, and this alternate. So this mutex semaphore will prevent race condition when multiple producer consumer access the buffer simultaneously, right? This is the pseudocode problem. Producer do while loop. So producer, in case of producer problem, we have to produce an item, right? So item will be produced first, right? There are two types of operation. One is wait, another is signal. There are